wrote down, did anybody write down this R square around C numbers or not? Huh? Why don't you do it? I'm asking you for the third class to keep track of all numbers.
I'm keeping track for,
okay.
Yes, I wasn't able to calculate R2 for a couple of last methods. It's somehow produced an error.
Strange. A square? Why? So?
Don't know.
Okay, who keeps track? Huh? For everybody. No, R square is actually doesn't. It shouldn't be, because R square you compute the relation between y predicted and y observed. So you have this.
For RMC.
Well, maybe default summary didn't work or something. I don't know. Default summary is maybe you just named it. There are several ways to do it. So who has numbers? Tell me. Nobody has numbers? This should be punishment. Why don't you have numbers? Nobody has numbers.
For linear,
You missed last lecture. Okay. Nobody have numbers from the last lecture?
From Mars model?
From Mars, from SEM, or KNN? You do have, okay, fine. And?
The Mars model MC is all coincidence too.
But compared to all others, is it better compared to linear, say?
Compared to linear, it is close to little bit higher, but close. And that's where it is.
Yeah, that's true. It's pity you don't keep track, because this is the most interesting part to compare models. It's not. So Mars model is not necessarily better than the linear model, but what's nice about Mars model, you can have predictive importance. You can have. Did you plot these graphs? This is a tuning model. When you look how many, actually Mars can be two types. It can be first order model, it can be second order. First is a linear approximation, second order is a quadratic approximation. And this is the number of terms. So when you run this in caret package, number of terms counts as a tuning parameter. Tuning parameter meaning that how many terms in Mars model are used. And actually having many parameters like 220x, you can be down to 30 or even 38. So this is a simplification. This is the first advantage. And the second advantage is that you have a nice at the end, you have a nice representation of the dependence of one variable against the other. So Mars model is that it's actually build dependence one by one. It's add one by one predictors to produce the whole outcome. In terms of analyzing predictor importance, it's very convenient and easy to interpret. And if you did it right last time during the workshop, let me show you what you should have done. I didn't send slides around, right? Did Anton send you slides around? No? You have it. Oh no, you don't. Did he send you around the slides? Okay, I will repeat for everybody to have. Okay, so if you do it, this is what you, there is a convenient function which is plot Mars fit, plot mod. When you can plot dependence of an outcome from the variable one by one, so it can generate you this kind of plot, which is if you do analysis, this is easy interpretable because you can see how outcome depends just on a single variable. This is one of the advantages of this analysis, that you can have this variable importance. Here is variable importance.
How do we interpret the previous graphic? Can you explain the previous? So we get the prediction only using one.
That one? Yeah, so one by one. So the marks work that it takes just one variable, say, sum, and do a approximation with a piecewise linear. Doing just one, looking for the one point that would kind of be an angle between two lines. Do approximation. Then it adds another variable, again looking for the piecewise function that will do it better. And then combine them. So actually each variable is split, you can say, in two lines, in two dependencies. So you have one linear relationships in this region and the second linear relationship in this region. This is a piecewise linear approximation.
The target or
Of the
this
target.
prediction?
Of the target. One predictor for the target. For each predictor, it is done separately. That's why it's.
But we get very different predictions.
Yeah, that would be different relation, but that's what you have at the end. This clause that you have at the end, you have this piecewise linear relations for all predictors included, but not all are included. So it's only a subset of predictors, because we have 228 and only 38 predictors were chosen. And there is a linear algorithm how to choose which one. And then you can rank them as important. You can rank them as important with the variable importance function. Here is variable importance function. And you can see, for example, that molecular weight is the most important, following the number of non-hydrogen atoms, surface area, number of hydrogen, number of oxygen, etc., and downwards. So this is, sometimes it's convenient to run Mars only because of the variable importance analysis. It's not because the model predicts better than the other, just because it's easy to interpret. Not only you can have variable importance in random forest, for example, but you cannot see the real random forest regression. You can see you can have variable importance, but you cannot interpret. Here, for each variables, you have a function of dependencies, and this is when it does make sense. For example, you can we predict solubility, and you see, okay, when I have molecular weight less than 5, then my solubility depends on molecular weight like this. But when my molecular weight becomes more than 5.5, then my dependency goes more down. So this is understandable, right? Because now because you understand, okay, if my molecules are lightweight, then I have one dependence. If my molecules are heavy, then I have another dependence. So it's kind of, there is an interpretation, there is a biological or chemical interpretation for the subject. The same here too with the surface area. When my surface area is below some critical value, I don't have dependence on solubility at all, and then solubility begins to grow after a certain threshold. Again, it's easy interpretable, because it's not only just the ranking of the predictor, it's also the functions we have. And functions are piecewise linear. This is why it's Mars. Multivariate adaptive regression splines. Splines is these pieces, this piecewise functions. It's called splines. That's why it is Mars. it's nice to know about this model. Okay, this one is, or this is what is my comparison here, right? So you see it's neural network we have not done, and this is what actually you see here, that RMSC is compared, well, forget about neural network is not really correct, because it's, I run it on a small number of iterations and nodes, but say RMSE here is 0.72, RMSE here is almost comparable. R-square even slightly better than just linear model, just linear. It's not better if you compare it to the elastic nets. Elastic net would be better, but still, you know, it's comparable. It's not we run Mars because it's considerably better. We run Mars because we want to go deeper into the structure of the dependencies. We want to find out what are the real dependencies. Support vector machine. This is, I don't know how you were, let me go a little bit over theory on support vector machine to repeat here. Okay, support vector machine. Support vector machine is a nice algorithm. So it's quite kind of powerful. You will find that it is used in many applications successfully. Did you have a problem, by the way, running SVM last class with some, or it worked smoothly? Did you have problems running SVM last class? Huh? No, but it didn't produce error, no? Because what kind of kernel did you use? Radial or some other kernel? Radial. Because you know, the year before, the reason I'm asking, the year before, we got a problem running this VM. It produces error was something in the package. The problem was in the package, the package, which were fixed since that time. Okay, what's the idea of the support vectors? Let me go again. So we have data, right? The data considered as a vector. Because we have the data with many predictors, and the numbers in front of any predictors considered as coordinates, right? If you have 228 predictors, we have 228 coordinates. And in mathematics, we can call each point, every point, as a vector with 228 coordinates in the 228 space. Imagine that the idea of support vector machine. This is usual example for classification problem. And then it was because it was first invented for classification problems, and then was also shown, it was shown that it can be used for regression analysis. These are points, these are data. This is example, of course, in two-dimensional space because it's easy to visualize. The idea was in classification task not to use all data in your model, but only data that lies close to the margin, on the margin, which is support vectors. Why is it so? Because this is actually easy. The more we separate it, the more the points are separated, they are kind of easy to distinguish. These are problematic because they are close to each other, but they also lie at a certain margin. We call it, this is a margin that separates two data sets, two points in our space. So finally, we built a model not on all data that we have, but on a specially chosen support vectors. The same with regression. I will you will, I don't know if Anton point your attention to this, but how to use it, it's already, so all regression tasks, they use kind of, they call it epsilon intensive function, that all the dots that, which is zero in a certain area of parameters. It is zero in a certain areas of parameters because we want that all dots that are lying inside this margin, for example, if there are dots that are here, we do not take them into account. We don't want any data that's lying inside this margin be taken into the model too. So we don't want these data that are out of this margin, and we also do not want to use dot or data that's inside this tube or tunnel. So finally, we use only support vectors, and mathematically, it is realized. We again looking for the combination. Actually, we again looking for the combination, but we use it. We calculate this coefficient with the use with this function, which multiplies by this predicted and observed y. You see, this is here, and this is a cost parameter, which is you should use, or you used it last year to as a tuning parameter, cost parameter, and also this is we penalize large residuals. So we do this penalization. So this is a mathematical formula for SVM, and this is actually to show you that linear support vector regression is also a linear combination. Again, it's a linear combination, but linear combination is a kind of tricky. So if you compare it to the linear regression, we just find this, in linear regression, we're just trying to find coefficient in front of our predictors. Here too, we would like to find coefficient in front of our predictors, but we do it very, very kind of sophisticated. We do some transformations of the space that we rewrite it as a double sum, which is here the combination of the support vector. You don't have to really understand it, it's just, you can read it maybe closely in the book, but at the end, what you, let me see you. Here is what you end up. So what you are looking on the linear combination of support vectors. So our support vectors ended up here. Our support vectors ended up in the sum, and actually you finally build a regression on a support vector, on a especially, maybe we should rerun it in a workshop that you see the output of the model, or I show you the difference. Again, in regression lines, so we always define some margin. And the points that lies inside this margin or close to this margin are just excluded from the this area plus minus epsilon is called funnel. So this is all our points. And we see that this crosses the points that were not included in the model. So the final model is built just on the less data points, and the points that are here that actually the points that produce less red. This is SVM residuals. And here is an example that show you that least square, you remember this is just normal regression line. In SVM, this is a difference of, that could be difference in line, outcome versus predictor. This is just one predictor that SVM could behave better than just linear regression. So it can kind of be tuned so that at the end it works better. At the end it works better. How it's calculated, there are, SVM is usually, the other tuning parameters in SVM is a kernel. The kernel can be polynomial, radial basis, and hyperbolic tangent. So as I found out, you finally use radial kernel. This is again, illustration that ordinary regression line is here, that SVM outperforms in some tasks, say ordinary regression lines that they, or some other methods. So of course, because of this inner structure, let me let me go to the workshop and find out that you've done everything correctly as I expected. So this was this is what you've that's what you should done last class, right? So first, this is not a carrot package. This is a kernel package. Did you have problems to install it, or it went smoothly? It went okay. So in the kernel, as it's so you have three different variations for the kernel. So you can use SVM radial, SVM linear, or SVM core. Again, for you to apply SVM, you just need to know how to install packages, right? So first, you have to understand the tuning parameters and the packages. Again, so we apply it to the solubility data. Here is the kernel RF dot, RBF dot, and we supplied epsilon parameter and one cost parameter, and you had an outcome. And this is SVM with train. SVM with train was run like this with the SVM radial, so it took some time, that's correct. Here is the outcome you had. Okay, this is just one cost parameter, but it does not, unfortunately, it does not, at the end, it should tell you the number of the support vectors, and I didn't print it out. Can somebody rerun it, or maybe there is somebody having it in the as a model, saved as a model, because I did not print it out. There should be, with all this outcome, there should be print out how many support vector did we use from the final data. Can we rerun it? Is it here? No. Can we rerun it? Can you rerun it from this? You can do tune length not 14 but just 2. Make tune length 2. That would make it much faster. If you make it tune length 2, it will be considerably faster. Not 5 minutes by 5 minutes divided by 10.
Well, actually, I already have
You already have
result with tune length 14, so that's all the output.
Support vector, it does not tell you.
Yes. Well, but we have like that with predictors, but I guess it's not if we are.
No. It does not say how many vectors. Machine is ready, 95 samples. Sample sizes No. It was somewhere. I forgot. It should be. It was somewhere reported how many support vectors were used in the model, in the final models. No preprocessors, the samples, sampling, chain parameters. Where was it? Maybe with the other kernel, no? Should be. Okay. So, maybe it's in classification, not in regression. Maybe in classification test. Okay. This one did not work for you. That's where. Because it's maybe the function are square, that there should be some syntactic error. Okay, so, well, KNN is an easy model. I don't think it should have a question. Let's move further to the neural network. Okay. Neural network. So which was actually originally the part 1. Neural networks, very famous, very looking kind of a little bit scary, but it should not. And you can see that neural network is nothing complex. It's just a complex complex in linear combination. So neural network, as you might guess, comes from the analogy of the neurons, and neurons in biology works like that. To pass on an excitation, it collects signal from many different neurons, like this, and this. There is a fire in it, but the decision for neuron to fire and to pass on a signal, or to stop it, block it, and not to pass it, is made up based on the kind of amplitude of the stimulation, of overall amplitude, or sum of all amplitude of excitation of all other axons. This is the same idea was used in the neural network, which actually started the idea to use this kind of logic for the computations and the calculation started as early as 1943. There was a first conceptual model that it's possible. And the question is, so some tasks are difficult for human and easy for computers. And some tasks are easy for computers and difficult for humans. For example, what are the tasks? Simple for computer but difficult for human this is a binary operation, right? To make, but you know, these binary calculations that all this digital machine are based on, they have a different logics, and we know perfectly what is this binary logic. And simple for human but difficult for computers recognizing it. Though nowadays, actually what I learned just last Saturday when I was on this, I was on the School of Economic, what is called science, not festival, or you can say Festival of Science, was on Saturday in Digital October, and I heard the presentation from Microsoft. And the guy told that now actually, last year, 2017, neural network made by Microsoft recognize faces 1% better than human. So now it's actually it's not already true. So now this percentage what recognizing faces, so you have a photos of many faces, and you can the program can recognize whether it's human or human, women, male, and even emotion, angry, perplexed, thinking, smiling, etc. So now the neural network that advanced at least. But okay, I don't want to see. Interesting that in 1957 there was a first simple model, and look at this simple perceptron. And the first publication in 1957, this very, very simple device showed that this simple device already can solve and learn and do simple tasks. And let us see what we can do with this simple perceptron. So imagine the device is just one circle. It has two inputs, input 0, input 1. There will be two values input. So here is one input gives you a number, and the second input gives you a number. And the output also would be one number, and one number we decided that output is just the sign of the sum of the two values that you assign, either positive or negative. And if the sum is positive, we decided to activate it. If signs like activate neuron to fire. If the sum is negative, let's down it and shuffle it. But then we do a little bit addition, and we do weight. So we not just enter simple numbers like and integer numbers. We multiply it by some weights. Let be input 0 multiplied by weight 0. Say, for example, here input 12, weight 0, 5. We do this input multiplied by weight. We have 6. We have input 4. We have weight minus 1. We multiply it. We have minus 4. Then 6 minus 4. The result is 2. And sign of 2 is positive, then plus 1. Okay, and then you be randomly sent numbers to this processor. We randomly send numbers to this processors, and the output is either plus or minus. Right? Okay, so what can we do with this? What we can do with this simple perceptron? Actually, it appears that with simple perceptron, we can draw a classification line. How? For example, so if you have a space filled like this, and you have dots, and then you just submit this dot, and your two numbers just coordinates of your dot in a space. So that would be x coordinate, that would be y coordinate. And then here you can have the line that you would like to put a classification. This is what I draw. This is my line. But I want to teach the simple perceptron that have just two inputs and one output. That's it, nothing else. I want to teach this perceptron to recognize numbers, whether it's above the line or below the line. It's appeared it is quite possible. So I draw this line, and I try to kind of, for example, there is a dot with the coordinate x and y, and I submitted it to perceptron, and I have some output. First, how how my perceptron should divide. Let it guess for the first time, because for the first time it doesn't know if it's positive or negative. Let's suppose then 50-50 chances that it will be right or it will get wrong. But then, after it learns if it's right or if it's wrong, I will correct it. If it's right, that's okay. If it's incorrect, then I should invent some kind of adjustment, how to say he's wrong, that this perceptron is wrong. And this is adjustment. I will invent an adjustment in case of error. And these are four combination of how can I correct them. For example, if perceptron decided that it's -1 or negative, or actually I know that it's my daughter's negative, the answer, but he guessed it -1, there is no error, right? Or there was a -1 and he guessed that it is +1, that -1 minus this number would produce an error -2. The same wise, if it's 1, but he guessed it -1, that this number minus this one number produces +2. And again, this is 2 + 1 + 1, and then we have an error of 0. Let me, what I would like to do, I would like to make some corrections to the coefficients. Because remember, my initial perceptron, here is my initial perceptron, is just combination of weights and inputs. And if the perceptron gets it wrong, I want to make adjustment to this weight. Just create some delta weights. But according to some rules, what are the rules to do this delta weight? This delta weight, let's this delta that I'm introduced, this delta weight, would be error that I calculated according to the strict arithmetics. I did not invent anything multiplied by input. So this is true. Then I will have a new weight. A new weight will be weight plus this delta weight, or you can write it weight plus error multiplied by input. And I can also actually do some modification and multiply this error by input. I can introduce some number. This is how well I adjust, called learning constant. Meaning, what meaning? For example, I have a how big I can, or how big are my changes. For example, if I have a weight of 5, for example, how would I like to change? What would be my next iteration? I'm wrong. So with weight 5, for example, I have 5 multiplied by x1 plus 10 multiplied by x2, and I'm wrong. Next time I would like to try new coefficient, but this new, and I say error is -10. It's a big error, right? So I can say, okay, well, if error is -10, let's try to use next time 5 minus 10x1 plus 10 multiplied by -10x2. Let's try this, then I will have -50x1 minus 100x2. And this is, this is a big change, right? So first, maybe I'm again wrong, and this would be wrong. So from this equation, I come to this, and these are, well, this 10 times bigger because they're, but I say, okay, I don't want to move that fast. Let I introduce some learning constant. Let's I do it like this, 0, 0, 1, and 0, 0, 1. And then I would, next time I would try not 50, but I would try 0.5 and 0.1. This is what and then I actually, you see, so I add to 5, I add this adjustment, and next time I tried 5.5 x1 plus 10.1 x2. So kind of I tuned a little bit my coefficient. I changed them, but not right away to the other number, but just tuned it a little. And how do I tune? I define by this learning constant. And you see, I'm just going to be patient. I'm leading you to the neural network. Now I would like you try this on this page. Try to type. Maybe try natureofcode.com chapter 10 neural network. There is an animated figure. I would like you to see it yourself on your screen. Let me also go to the web. And how do I go? Let me see. Let us try to find Nature of Code. This is actually a nice book, and it has a chapter 10 that devoted to here. Chapter 2, let me show you Nature of Code. Nature of Code, I'll show you the link. Again, go to this page. It's actually, you can read it. It's what I'm trying to use, that simple, where is it? Simple person, did you find it? Oh, no, I cannot. Did you find it? Nature of Code. Chapter 10 neural networks. You can Google maybe natureofcode.com plus chapter 10 neural networks. Did you find it? Try to play this image. Just scroll down. So the exam, what's the idea? The idea is that simple perceptron having just two inputs, one output, like this, with a simple logic and simple equation, already can be trained. Where is this picture? To draw classification line by learning. That's important. You see, just linear combination, all strict, just simple arithmetics. Simple arithmetics, nothing less. Where is this? Here. Are you there? You see? So it's actually, this is what we expect. This is what we want. This is our line. This is our classification line. So every point above the line is a black. Every point down the line is an empty circle. And the by applying just this scheme, as I told you, just adjusting weight after many iterations. So it starts what it does do. Okay, you see what it's doing. So when it gets it right, there is no error, there is no adjustment. When it gets it wrong, there is an adjustment. And finally, you know, it's moving the line. This is first to draw the line and compare dots. So these are problematic dots that's still on the border, right? It doesn't get it right. So it's looking for an angle of the line. This is is learning. This is already neural, it's not a network, it's just one perceptron. Okay, good step. You see? Okay, if you're here, so with random, depending how do you start, and depending why does it, what do you think, why does it go in like this initially? Hmm? Yeah, maybe because the learning constant is too big. When learning constant is big, you kind of going from one extremity to the others. You do not do this small adjustment, you just do big steps of learning. You go backwards and forward. You see? And here, they actually also have a simple code how to realize it. How to realize it. But here. But is it clear now? No? Just simple. So this simple device can already solve 2D classification tasks. Is it not amazing? Hmm? No? You're tired. I think it's amazing. I don't know. It's just, you see, simple linear combination. It's very simple. Simple rules and no magic, right? No magic. Just straightforward. Simple. As simple you can read it. Simple as I told you. Just solve the rule, compute the errors, do weight adjustment. New weight is weight plus delta weight. You can introduce learning constant. And then you can train this perceptron to do this classification task. And then, of course, neural network is just a combination of all this. Okay, so you can read it again for those who are interested. Let's stop it. So you have a realization, you can, there is a steering perceptron that do the more complicated task. And you can look it up at your own if you're interested. But this is, you see, this is input and output. But now this was a publication of 1957. Just let us imagine, what was in 1957? Do we have computers? Not at all, right? People who wrote this, though this is, where is my link to the publication on the subject here? Cornell Aeronautical Laboratory, 1957, Frank Rosenblatt. It's all was, you know, pen and pencil calculation. Pen and pencil calculation, no computer simulation. Now you can do this computer simulation. And okay, here is our basic neuron, right? You can have as many input as you want, and all the inputs that comes into neuron, it's a linear combination. So linear combination may be a key word in all machine learning class and all machine learning course, because everything is built on linear combination and their differentiation. Okay, again, we have linear combination, but, and we have some. So then we have to decide what would be here, what shall we output, what should be output, and what should be result. They actually, the idea whether to fire or to not. And here is a different solution. We can do it stepwise. Stepwise meaning it's either 0 or 1. This is stepwise function. Stepwise function is either 0 or 1, but it's kind of plain, right? So we don't what? Meaning that if the number, what is meaning 0, 1? For example, I can make any threshold. I say, okay, if I have numbers less than 5, let it be 0. Everything that's above 5, the output is 1. Or any number, or 1,000. Say, okay, if my sum is less than 1,000, the output is 0. If my sum is more than or equal than 1,000, then the output is 1. But then I can do it with the sigmoid function. And the idea to use sigmoid function again comes to biology, that it's not just like plain, right? 1,000 less or above. It's kind of smooth transition. And this function that you see is called sigmoid activation function, which has an explicit formula. Explicit formula is this. The nice thing about this formula that you can differentiate it, and when you differentiate it, you have derivative. It's actually, you can write it as the function multiplied by minus with the same function. Again, nice mathematical thing. It's continuous functions. And sigmoid function, so now you can have, this kind of, again, threshold. So it's not just -1 and +1. You can have this 0, and then you can vary your threshold. You can say, okay, I activate my neuron over threshold of 0.9, or I activate my neuron up under the threshold of 0.75. So this is again okay, this is just one neuron. This is complication, multi-layer neuron. Now we just do not have one perceptron, right? One. The neural network is just combination of many, and we not only have many neurons, we have layers of neurons. What does it mean, the layers? The layers mean that there is an input neurons. There is a neurons in between, this is layer in between, and there are output neurons. And as you can see by these lines, that the numbers in this neuron, they come from all neurons from the previous layer. You see? What does it mean comes from all neurons? Meaning that there is a linear combinations with coefficients. So you take, we are in the world of numbers, and these neurons are all numbers. In the end, they're all just numbers. And you have all these numbers multiplied by these coefficients to some numbers, you sum it, and you get a new number here. You get a new number here, you get a new number here. Then to the output, again the same. You have all these numbers, they multiplied always by the same coefficient, because these lines mean linear combinations from all these neurons to here. And coefficients, what are the coefficients is the most complex things. We have to find them. So all the time you spend, the neural network is training, and this can be days and days and days, they're all just looking for this coefficient of linear combination, and that's it. Nothing mysterious. So these are all, this is what's the general schema of the neural network. And how do we do this? Let me see, let me go to this, I want this general schema here. How do we do this? How do we know this coefficient? The coefficient is come from adjustment. How is it training? Maybe I didn't say about error. Because it's a supervised learning. Supervised what? Supervised meaning that we always know the answer. When we train the neural network, we always know the real answer. And then we know error. For example, it's a regression task, right? Regression task meaning we know the exact number. And then we do all these calculations of linear combination. So the first run of the neural network, all coefficients are fixed, right? Some numbers. we do all this calculation with number, this linear combination plus linear combination plus linear. We did it and got the numbers. Okay, and say we got this solubility on our data. And then we have the output. And then we compare what should be the numbers. And of course, we did not guess it right for the first time. We had the error. And once we have the error, we go back. We go back, it's called back propagation, and we are updating the weights. Okay, we say we want other weights are coefficient in linear combinations. We need other weights, and we have the rule to tune the weights. We tune in them. And there is a formula to tune these weights. We are updating the weights. Then at a certain point we have to stop, right? We cannot do it. All this going back and forth, all this called iterations. And then we have to stop, and then we have to decide the number of hidden neurons. Hidden meaning that they're in the middle. This is input we see, this is output we see, and these are hidden that we don't see. This is hidden layer. We don't know how many layers, but we have to decide on that. And well, it's there are many strategies. How do you adjust coefficient? We can. This is a whole theory. Actually, I'm not going to do it now. But the only thing you this is actually the same as in perceptron, right? You have a new weight adjusted by some delta weight. And the delta weight could be a combination of, you can introduce delta through, adjust through the learning rate and through the error gradient. So how error gradient, not just the error, but the derivative of the error. So how far is your error grows, right? So you can use it, and it is implemented for you. And then here is the general scheme. And let us just compare. It's again, if you look at this, I showed you already this is for linear combination, or for PCR, or for PLS. It's actually the same schema. You have predictors, you have a new variables that are linear combinations of your original predictors. At this point, it's the same as, say, PCA, principal components, also new combinations of linear predictors, or PLS components. Remember partial least square that we adjusted. Okay, new variables that are linear combination of your original. Your hidden neurons are also the same hidden new, or the same variables, the same new variables that you work with. They're just linear combination of original predictors. And then you build an outcome. You build an outcome as a linear combination of your original predictors. Of your, not original, I'm sorry, a linear combination of your new variables. So the only difference from the linear, you see, is that you introduce a sigmoidal relations to here. This is the only non-linearity introduced. First you do. So it's not just linear. Linear would be this. Plain linear is what I wrote in brackets. But you multiply this linear by sigmoid. This is the only non-linear. This is called activation function. And when you run neural network yourself, the activation function is not necessarily sigmoid. This is a tuning parameter. We'll have time probably to look today that there are different, you can tune it. So this is it. So once you remove this G from here, your schema does not differ from PCA or PLS at all. It's the same schematic. So you see, that's what I told you at the beginning. So all machine learning is just linear combinations. A neural network is again, the complications are just in time, so it's nothing, eventually, it's not real a black box. Of course, machine learning is a black box. So SVM may be more black box than the neural network. It's all clear, it's nothing mysterious here. It's just the complexity comes from the number of coefficients you have to calculate. That's all the machine times comes to. So now this deep network is just, you have not one layer, but many layers, right? What is deep learning? That you introduce not just one layer, but say 10 layers. And each layer is a linear combination of the layers before. Again, you can play with activation functions, you can play with some different, you can play with learning constant and hidden variables. This is what I already emphasized to you, that this is only, and in regression task, again, neural network also can be used either for regression or for classification. And output, for regression task, output is a linear combination. So in terms it's a linear modeling. The only trick is above this line. The only trick is above this line. You can see it's PCA with sigmoid function. Or, no, PCA, there is a rule. There is a just different rule to find the coefficients of this new variable. That's it. That's as simple as it is. But complexity, as I told you, comes from the number of parameters. So how many parameters in the neural network we need to estimate? If P is a number of predictors, the first input layer, and H is a number with hidden unit, then H multiplies by P plus 1 plus H plus 1. That's the number. Say if we have 220 predictors, then we have depending hidden neurons like 10. Here is the number. So for solubility data, 3 hidden units you have to calculate, say 191 parameters. 5 hidden units, you already have to calculate 1,151 parameters at each iteration. And this is, okay, this is probably, this is what we will get. This is comparison again. This is comparison. PLS, linear combination to correlate with outcome, and neural network, just linear combination multiplied by sigmoid function. Remember this task, linear combination, when we wanted to predict people with knowing shoe size and times to go to work, predict height and weight, or vice versa. Now the one for parameter. Do you remember this example? So this is again all this schema. PCA is just linear combination to reduce variance. There are different restrictions. What maybe we can do it up. Yeah, we have 8 minutes. This is a nice entertainment. TensorFlow from Google. Let's go here. Before we come to the workshops, we run neural network after the break, but now let's play with TensorFlow from Google. If you type TensorFlow in Google, you will get directly to the page. Let's go tensor type TensorFlow. TensorFlow. Here? No, not here. TensorFlow from Tensor. No, which one is Playground TensorFlow or Playground TensorFlow. Playground. Here. Playground. What's nice about this? Okay, you can now try to solve different, this is a playground in order to feel the parameters of the neural network. For example, there are two problems types. There is regression, there is classification, right? Let's put regression. Regression, maybe classification is actually more obvious, right? But, okay, either regression or classification. Then, you can play with different number of output and you can do it without any hidden, well, actually one hidden neuron is required. Then you can also play with the number of output neurons. Then you can see this learning rate. So how fast we learn or how slow do we learn, right? So here is by default is 0.03. And actually we can try different number like going back and forth. You can see what would be the differences in put learning rates. So your coefficient would be adjusted, from that to that, and you can see this fluctuation. You see the activation function. So sigmoid, we just started, I told you there are 4 more that can be. And actually in real neural network there can be much more. Then regularization and mean penalty for errors, right? So let's do it none as they, so we can have it, or and regularization rate, we can leave it 0. And you just try play and see what happens. Sometimes it's impossible to solve the problem. And this is epoch. Epoch means number of iterations. The idea, you see this in regression task. This color coding means that you have real dots, right, which have values. It's actually the red is negative here and blue is positive. It's kind of counterintuitive. I usually use if it's red it's hot, if it's blue it's cold, but here's vice versa. If it's -1 here, it's negative. And the dots are the real dots, and this is what you predicted. So when the red color covered red dots, meaning this is correct. So let's see, and this is initial. You can put on initial distribution like this, for example, and like this, and add this. So you see, you have 2 initial sets. So you have the next one distribution like this, here distribution like this. This is all 0, right, or all lies positive. And this is distribution of points. You can play with your own right. And then when you start playing, you see the adjustment. Actually, it comes very quickly. Learning rate, it comes very quickly to the right solution. You can, if I do learning rate 10, for example, okay, reset. You see, learning rate 10, so it's not right. Learning rate 10, and probably, we'll see if we find the best solution. What is it doing? I wonder. So why weight is non-applicable? Why so weight is non-applicable? Something is wrong. Actually, you see, you can see different initial distributions. No, something is wrong. When you pull over the mouse and you see the weight is non-applicable, then something is wrong. Okay, here's to understand. So it doesn't want learning rate 10. If learning rate is 1. Well, learning 1 is goes, triangle, goes. And if you pull over the line, you can see the weight always. Here weight 031, 031. Here is 029, 34. You see how the weights are adjusted. And here too. So the color of line represents the numbers in weight. This is regression. You see its learning rate is 1, and it still cannot decide on the boundary. It's always going back and forth. And the reason 1 is too big, because all the coefficient is less than 1. Is less than 1, learning rate is 1, they all, going back and forth, back and forth, back and forth. And probably it won't stop, so the adjustment is too big. Then I put learning rate is 0.1, reset it, and do it. And this is already more stable, you see? So this network is more stable. So learning rate is important. If I put it 0.3, reset it. This is also true. And 1 doesn't work. And when I put it 1, okay. And learning rate is 1, it just does not. So you cannot learn with that big number for this. So it will never probably get stable because 1 is too big. You can also, did it work for you? You can try classification too, it's interesting. You can try classification task. And you can see that two-dimensional classification would never solve with one hidden neighbor. You have 2 inputs, so this is what your classification and the arrow is big, but probably that's it. You cannot do it better. So to solve two-dimensional classification task, you need at least 2 neurons here. Let's see now if we can do it. Learning rate is again. See, it's trying to find a boundary, it doesn't work. Again, because learning rate is 1. Let's see, learning rate is 0.1. If it works. So what's going on? You can look up at the coefficient. So, okay, probably will do. So the desirable, it should encircle all these blue dots. Now it's stable on the arrow. For some reason, I actually cannot tell you why. I cannot tell you why. So, but the problem is not solved. Let's see if we wait. No, it doesn't actually help, right? It's kind of stable. Okay, but if I add additional neuron, will it help? Yeah, it does. You see? Just adding 1 additional neuron, this is ridiculous. It does. So this is initial distribution, learning rate, and it's very quickly find a solution. But if I remove 1 neuron, again, it doesn't find the solution. You see the tricks. Doing something. Trying to learn, poor guy. Not a guy, or girl. Trying to learn. Interesting. Okay, so now you know it, you know how to adjust. Now we'll do a break, and this is a nice entertainment. to see how the parameters, number of hidden neurons, actually you can also add layers. You can add layers here, you see? We can introduce, so let's see if layers help. Interesting that here even layers doesn't help. It's just, okay, let's do a break and then come back at 7:45 for the workshop. Okay? Let's see, I'll leave it running. Let's see if it helps. If it doesn't. Okay, 7:45.
Я просто хочу стащить. Сталкинс. Классификацию делаем. Я думаю, что у меня так легко. Окей. Да, то началось. Что такое? Ну вот он пытается вот эти вот точки, как раз он пытается понять, а где находится где находится синий, где находится оранжевый. Да, и он пытается определить, какие точки, какая часть пространства синяя, какая часть пространства оранжевая.
Он что такое говорит? Сказал такого слова. Нет? Нет. Реально? Зачем ты